driver of the Zynq Octoscale Plus MC SoC. Television, which is a huge driver of 4K content and video conferencing on mobile devices. The need to capture and transfer vast amounts of video is growing, so we developed a device family to address these advanced requirements. Standard video codec capable of 4K encode and decode up to 60 frames per second. We're happy to announce that we have the first ZU7ED devices up and running in our labs on the ZCU106 development board. Let's take a look at the Zynq Octoscale Plus MC SoC video codec in action. We're taking a 4K H.264 compressed video stream at 60 megabits per second from a USB stick onto our ZCU106 development board. The ZU7ED devices decodes the H.264 data and streams the raw video to the display via the integrated display port. The GPU accurately decodes the 4K H.264 standard as shown in this high-quality video. Simultaneously, the newly uncompressed video is being encoded to H.265 HEVC standard at 4K at 10 megabits per second. This highlights the ZU7ED's transcodability, compressing an H.264 50 megabits per second stream into a H.265 10 megabits per second stream in real time. Transcoding results in a 6x file size reduction, reducing bandwidth requirements for high-definition video transfer. The H.265 data stream exits the ZCU106 port through a hardened Ethernet port. The second ZCU106 port accepts the stream, decompressing the H.265 data and streaming video via the display port to the second monitor. Here we see the same high-quality 4K video reproduced after real-time transcoding on the Zynq device. Looking at both monitors, we see almost no loss in quality between the original H.264 stream and the newly compressed H.265 stream, with very low latency highlighted to the simultaneous transcoding capability of the integrated DCU. Today, we've demonstrated the newest Zynq Octoscale Plus MC SoC ED devices, featuring a high-performance integrated video codec alongside powerful processors and integrated peripherals designed for multimedia applications. Using only the hardened engines and peripherals of the ZU7ED devices, the integrated programmable logic is available for product differentiation, optimal for video processing algorithms, filters, overlays, and custom interfaces. With the ZCU106 development board and GStreamer multimedia framework support, we have everything you need to accelerate your multimedia design with the Zynq Octoscale Plus MC SoC ED devices. Visit Xilinx.com to learn more about the Zynq Octoscale Plus MC SoC ED devices. Thank you. Hi, my name is Whitney, Senior Product Manager of Embedded Vision and SDSoC. We're very excited to announce Revision Stack, which is a software-defined development environment for embedded vision. Here, we're going to look at the demo doing computer vision, machine learning, and sensor fusion in a single thing and SoC. We're showing a number of different values with this demo. The first one being reconfigurability. We can combine computer vision, in this case stereo vision and optical flow, together with machine learning, including CNN and pedestrian detection. And then sensor fusion for multiple sensors from ET, USB 3, and even file inputs. And then we're removing the major barrier for wide adoption, which is software-defined environment and industry standard framework and language. Okay, now let's look at the demo itself. Here, what you're seeing is Zynq SoC, the development kit called ZCU102. And the setup we have here is two different sensors. One through MIDI, which is connected to the state-of-art Sony IMX274 through FMC. And another one is a Stereolab stereo camera through USB 3. And then the Octoscale Plus MC SoC is processing both sensors simultaneously, applying stereo vision, optical flow, and machine learning. And the output of those three is blended through a video mixer and display on HDMI output. Now let's look at the screen itself. We position the screen so it shows real-time stereo, optical flow, and machine learning. And you can see that from a person looking in front of those two cameras. For more information on revision, please go to Xilinx.com/revision. Thank you. Hi, my name is Nicky, Senior Product Manager for Embedded Vision and SDSoC. Today, we're very excited to announce Revision Stack, which is software-defined development flow for embedded vision. Here, we're showing a demo of 4K 60 Hz optical flow, and it shows three major values of revision. First value is the state-of-art responsiveness. 4K 60 Hz optical flow is something unmatched by our competition. Indeed, it shows over 100x speed up over embedded GPUs and SoCs. It also shows our any-to-any connectivity advantage, connecting to the state-of-art 4K 60 sensors and also some different IOs as well. And then finally, we're removing the barrier to wide adoption, which is the software programmability and the industry standard library and frameworks. So now let's look at the demo itself. So here, what you're seeing is our development kit for Zynq Octoscale Plus MC SoC called ZCU102. And the setup we have here is a MIDI sensor connecting to the 4K 60 showing IMX274. And this is where the camera input comes into the chip and gets processed through 4K 60 real-time and optical flow, and output goes out straight to the HDMI at the 4K 60 rate. Now looking at the screen, which is showing the HDMI output, you see the person in front of the camera moving, and with very low latency, you see the optical flow being reflected on output. And this indeed is showing a pixel-wide optical flow depth at 4K 60, which is unmatched by anybody else. Now, for more information on revision, please visit Xilinx.com/revision. Thank you for watching. Next-generation RF communication systems features usable footprint and power, while at the same time increasing the hardware flexibility to address a wide range of use cases or radio variants.
Silence is integrating direct RF sampling converters into its MPSoC devices to create a new, all-programmable RF SoC family to address these challenges. In a moment, we will look at the performance of our recent 16nm FinFET test device. But first, let's review some of the benefits of direct RF sampling technology. Today's radios are typically implemented using analog signal processing techniques, similar to what's shown here. As we can see, the frequency shifting and selection is carried out in the analog domain, and the data converters operate at or near baseband. Some programmability can be added to these analog signal processing blocks. However, there are limits to what can be achieved in terms of flexibility and performance. But when we move the data converters closer to the antenna and carry out more of the frequency shifting and selection in the digital domain, we have a robust, highly flexible platform for radio implementation. With direct RF sampling converters, this is now possible, and we can take advantage of advanced CMOS technology to implement very power-efficient programmable RF signal processing. Let's take a look at the converter performance which can be achieved in advanced 16nm FinFET technology using digitally assisted techniques. The board you're seeing here contains a 16nm FinFET test chip with both 40 gigasample per second RF sampling ADC and a 60 gigasample per second RF DAC. The converters were evaluated across process, temperature, and power supply variation, and the built-in calibration and digitally assisted techniques delivered industry-leading levels of performance. For example, here we're looking at the output of an RF DAC on an FSW spectrum analyzer from Rohde & Schwarz. Excellent performance was observed for the RF DAC, which here is generating two tones centered at approximately 1.9 gigahertz and separated by 20 megahertz. The third order intermodulation distortion, or IM3, at minus 65 dBc illustrates very high linearity of the DAC. To test the ADC, a high-quality signal source, such as the FMW200A, also from Rohde & Schwarz, was used to synthesize both carrier wave and modulated waveforms. Additional analog filtering provided the signal purity required to evaluate the RF ADC. Data captured from the ADC was analyzed using FFTs implemented with LabVIEW software from National Instruments. Here we can see the FFT of a 1.9 GHz input zone sampled at 40 gigasamples per second. The second and third order distortion components are aliased in band to the first micro zone, as indicated by the red colored markers on your screen. Other distortion components shown are interleaving artifacts, which are greatly suppressed by the built-in digital calibration. For more details regarding the performance of the RF sampling ADC and DAC shown here, please refer to two papers published at the Gigahertz Converter session at ISCC in February 2017. The integration of direct RF sampling converters with our 16nm MPSoC devices greatly increases the flexibility of the RF platform, while at the same time reducing footprint and power. Please visit Xilinx.com to understand more about the unique benefits of the all-programmable RF SoC. I work for Stat, and we make machine tools. Machine tools that 95% of the time go into different engagements. And our machines make like hundreds of thousands of parts a year. In a way, you could say that we are selling contracts that go out of the door. And this means that we have some machines and technologies. This means that the electronic part of the business has growing in importance. And for that purpose, having reliable information that we can acquire is very important. I would say that the average rate of efficiency in an engine plant is not over 75%, which means that the system could be much more efficient. But to be honest, the first step was, can we be agile and collect what we want and nothing else? And we actually contacted with Sophie, they presented the technology to us, and everything made sense.
Sophie is a leading provider of multi-core for real-level FMS synchronization, data processing on the edge, sensor fusion, and cybersecurity for industry. We provide the logic or the operation that runs on Silence. So Silence is always in the middle of this business. We are using the Spartan RT7 SIG devices, even MPSoC. The SIG devices are the perfect technology to implement and type to link between the software world and hardware world.
We have the software part, and then we need the hardware part. For example, if you want to process vibrations using FPGAs, we need Sophie to help us to program the FPGAs to do that measurement on the accelerometer that's having the machine. And so I want to do most of this technical, and then ready to pay money for this with the potential business. If I take this to Sophie and systems that can allow you to learn how the machine is performing and how it should perform, I think one of these the box. So the final step, the extra mile is, can I help my customers use this box? Can I actually help them and show them you're going to gain this productivity, you're going to gain this savings in energy consumption? You have the good side. I think customers are going to demand more and more this kind of things. But technology does allow to more easily view potential for this kind of systems, so that's what I'm going to
Sophie is a leading provider of multi-core for real-level FMS synchronization, data processing on the edge, sensor fusion, and cybersecurity for industry. We have been in close connection with manufacturers of the automotive sector, so we have been learning what were the requirements about data.